taking its time. Here we go. It was somehow confused. Yes, I think it is. I'll just make sure that the
we switch,
yeah.
So okay.
That's all fine.
We can probably shift it now.
Yeah, it's all,
Yes,
it's all fine.
Okay, if you just want to take a seat down there for a moment, I'll do the necessary here. Well, good evening, ladies and gentlemen. Let me welcome you very warmly to the Royal Society and to this evening's lecture. My name is Peter Bruce. I'm the Physical Secretary and Vice President of the Royal Society, or one of the Vice Presidents of the Royal Society. So, as the name implies, I'm responsible for everything on the physical and engineering side of science, and of course the Bakerian falls within my remit. It's a great pleasure for me to introduce this evening's lecturer, Edward, or I call him Ed Hinds. The Bakerian lecture and award is our premier award in the physical sciences. So it sits at the top of the pecking order for such things, and only the most distinguished scientists receive this award. Just to give you a little background, the Bakerian Medal and Lecture comes from an endowment of Henry Baker, FRS, who endowed the Royal Society with £100. So you can tell it was endowed some time ago. And I want to read out the remit, if you like, of the award, what he required to get the words right. And so he bequested this award for narration or discourse on such part of natural history or experimental philosophy, so note the terminology of the time, at such time and in such manner as the President and Council of the Royal Society for the time being shall be pleased to order and appoint. You can guess from the language that it was, as I said, some time ago. The bequest was made in 1775, so the award has been around for quite some time. It's awarded to Ed Hinds, who is the 2019 Bakerian lecturer, for his outstanding work in quantum physics, especially the fundamental understandings such as the Casimir force, dark energy, and supersymmetry. As always happens, we were chatting before the lecture about something completely different in his interests, so I can say that Ed has a very eclectic range of interests. I'm sure he's chosen the one that's most appropriate for this lecture this evening. And without further ado, I want to invite Ed now to give his lecture.
Well, my lecture is called The Quantum Revolution in Science and Technology. That's actually a huge topic, so you'll be relieved to know I'm not going to tell you everything there is to say about this. I'm going to talk about electrons and photons, which are building blocks of the world around us. And I will describe a little bit about how electrons and photons behave and how they make amazingly accurate measuring tools. And I'll say how these tools are transforming society now through practical applications, and also how they can be used to address some interesting questions in science. So let us start with a question that has fascinated humans for at least 2,500 years, and probably a whole lot longer, which is, what is our world made of? And the answer, you know, is air and water and plants and motor cars and people and so forth. A huge variety of stuff. Now, if you're a scientist, your next question is going to be, yes, but what's it made of? And the modern answer is molecules. There are millions and millions of different kinds of molecules, and everything is made from molecules. I think you can guess the next question. Okay, but what are they made of? So if you look more closely into this picture, you'll see some red and blue balls, and those red and blue balls are representing atoms. So the molecule is made of atoms, and there are only about 100 different kinds of atoms. Although there are millions of different kinds of molecules, there are relatively few different kinds of atoms. The different molecules come about because the atoms can be stuck together in all sorts of different complicated ways. What's the next question? What are the atoms made of? Well, that's a really interesting answer. The answer is all atoms, all 100 or so of atoms, have this general structure that there is a center which is rather small and heavy, and that's made up of protons and neutrons, and then outside that is a big cloud of electrons. So that's just three things: protons, neutrons, and electrons. So I find it absolutely marvelous that all of this is actually just built up by assembling three building blocks, electrons, protons, and neutrons, into all sorts of different structures. Electrons give the atom its shape and size. They're the fluff, which is quite extensive, surrounding the tiny little center. Of course, the atom itself is tiny, but relative to the atom, the nucleus is very small. So most of the space is filled by the electrons, and so they give it, the atom, its shape and its size. And for that reason, electrons control a lot of the stuff going on around us. So if you ask about the smell of grass, where does it come from? It's actually determined by electrons, by the electrons that give the atoms their shape and size. The color of the sky, the hardness of steel, the wetness of water. Actually, I stopped listing because it's everything. Almost everything in everyday experience is due to the way that the electrons are operating inside the atoms that make up the molecules that make up the stuff. So if we understand electrons, we understand, well, a lot. But now, what's the next question? What is an electron made of? And the answer to this is rather interesting. It's an elementary lump of energy. And what I mean is you cannot chop it up into something smaller. That's it. It's a fundamental particle. And we call that a quantum. So that's the electron. And if I understand the electron, I understand a lot about the world. But there's something I've completely overlooked up till now, and that is light. What about light? Well, this is a rainbow. That's all the colors of light that you can see going from red to blue. Actually, some light is too red for your eye to be able to register it, but it's still light. So we call that infrared light or microwaves or radio frequency. That's light that is too red to see. And then there is also light that is too blue to see, called ultraviolet light or X-rays or gamma rays. It's all light, and it's not made of atoms. It's not made of electrons, and so if we understand the electrons, we don't yet understand the light. Next question, what is light made of? It's made of elementary pieces of light energy called the photon. So the photon is the little piece of light energy that you cannot break up into anything smaller. That is the quantum of light. So now we know what electrons and photons are. I want to talk next about how they move. Electrons and photons travel in the same way as waves travel. So I have here a picture of some waves in the sea, and they are approaching this wall, this sea wall here. The waves are coming to the right. Wherever you look, the waves are coming to the right. But you see on the far side, on the right-hand side of this hole in the wall, that's no longer true. Those waves are spreading out. So one thing that is true of the way that waves travel is if you confine a wave to a little gap, the wave will spread out. That's what's happened here. I should say, you won't observe this if the gap is extremely large. You notice it when the gap is of similar size to the distance between the crests of the wave. So this gap here is about the same size as the distance between the waves. And that's why the effect is easy to see here. I've just told you that electrons and photons do the same thing. So here is a beam of photons, which we call light, or a beam of electrons, and they're arriving here where there's a wall, but a wall with a slit in it. And provided the slit is suitably small, the wave which guides the movement of the photons and electrons will spread out like this. And you can see this. You just have to put a screen here, shine some light on this slit, put a screen here, and you will see that the blob of light on the screen is much wider than the slit. And that tells you that it's spreading out. And it's spreading out because it's a wave. I've drawn here some waves just to explain what I mean by these lines. The wave is wiggling like this. I want you to notice something now. The wave traveling down the middle here has a shorter distance to go than the wave going along there. And so you'll see that we're on a crest here. When the light arrives at the screen, the wave is a crest. But it's not so here, it's a trough here, and that's because that's a further distance. So where the wave is in its up and down depends upon how far it had to travel from the hole. Okay, so that is one property of how waves travel that I wanted to tell you about, that they spread out if you make them go through a gap. The second property is this. The waves can add or cancel, and that's called interference. That's the technical name for it. And it works like this. Suppose I have two waves and I bring them together in the same place. So here they are in the same place. And I've brought them together in such a way that the peaks of the one wave line up with the peaks of the other wave. What happens is you just get a doubly big wave. They add up. But what happens if I slide one of them over a little bit so that the peaks of one wave line up with the troughs of the other wave? Then the waves will cancel each other and there'll be no disturbance here. So that's interference. Light does the same thing. Electrons do the same thing. Here's an experiment where I shine some light, but this time I have two gaps in the wall. And again, I see a wide blob here, which we understand now. It's because when you confine a wave, it wants to spread out. That's what's responsible for the wide structure here. But something else is going on. It now goes light and dark and light and dark and light and dark. And that was first discussed by Thomas Young, a famous physicist, in the Bakerian lecture at the Royal Society 116 years ago. So we've actually, as you will see, we've actually come an amazingly long way in the last 116 years. What Thomas Young explained was this must be a wave. This light must be a wave because in the middle it's bright, and we can see why it's bright. It's the same distance from this hole to here as it is from this hole to here. And therefore the waves arrive in step. The peaks come together and the troughs come together. And because the waves are in step, the light is bright. On the other hand, if you go over here, I think you can see that this path is shorter than that one. So the wave gets sooner to this place from that slit, but it's longer from there. So this path is shorter and that path is longer, and so the waves have to slip relative to each other. And here they're out of step, and that's why it's dark here. And this goes on indefinitely until the light becomes too dim to see. So that's the phenomenon of interference, which was first explained in this way by Thomas Young. Now, what Thomas Young couldn't know, is that the light is made of photons. I told you that already. That's the elementary particle of light. It's made of photons. And he couldn't see one photon because his eye is not sensitive enough to see one photon. He might have been able to see 10 or 20 or 30, but he couldn't see one. But with a CCD camera, you can see one photon. So let me just say this. So this is about watching photons land on the screen of a CCD camera. The wave, which we've talked about, the wave feels both the slits, the wave feels the whole screen, but still the particle has to land somewhere, the photon has to land somewhere at a specific position on the screen, and here is a picture of the screen, and the photon landed here. So that little red dot is the arrival of one photon observed by the CCD camera. If we wait a little while, some more photons will land, and we can watch them landing. They land seemingly randomly all over the place. But actually, they are most likely to land at positions where the wave is strong. And where the wave is zero, where there's perfect cancellation of the waves, the photons cannot land there at all. And over time, you'll see this pattern build up into the sequence of stripes that I showed you from the young Bakerian lecture. Interesting thing about this, which was very hard for scientists to become reconciled with when it was first understood, is that you cannot know where a particular photon is going to land. The act of the screen registering the photon chooses a place, but you can't know ahead of time what that place is going to be. Strange but true. That's the way it is. Okay, so now we've talked a little bit about wave behavior of photons and electrons. Now I want to tell you an idea about how to use that to do something. And this is absolutely fabulous, very powerful idea, and it's called the interferometer. It means a gadget that uses interference of waves. That's what it is. And here is the idea. Now, later in my talk, I'm going to tell you about 3 different interferometers. So I know that it's warm, and you're probably starting to nod off, but this is really important. So have a think about this. An electron or photon comes along here, and now we have something called a splitter. And what the splitter does is to make the wave go in 2 different directions. For example, if this was light, if this was a beam of photons, everybody knows how to split light. You just have a piece of glass, and part of the light goes through, and part is reflected. That's all I'm talking about. Up here, let's arrange to have some mirrors, and the mirrors will deflect this wave around so that it can come back and cross over the wave that was transmitted. And in that place now, if I have another splitter, I can do something interesting. Or maybe it's better if I call it a combiner, because its job is to combine the light that went straight through, that's the lower wave here, with the light that took the long path here. So after this combiner, if I pick the right position for the mirrors, I can arrange for these 2 waves to sit perfectly on top of each other, and now we know that they will interfere to produce a doubly big wave. And the same positioning of this mirror, which makes this be so, also makes the waves coming out here cancel exactly. And so now I have a question which is not to be answered by anybody with a degree in physics. If I put a photon in here, where does it come out? Does anybody want to shout out and tell me where it comes out? In this case, because I have arranged for the waves to add up perfectly here and cancel perfectly here, I know that it's bound to come out here, because it will only come out where there is a wave, and there is no wave here. There was a component coming down here from this path, and another component that took this more complicated path, but I've arranged for them to be perfectly cancelling each other, so the wave is 0. And because the wave is 0, the photon is not allowed to go here. It is the same reason that in Young's Bakerian lecture, when he showed the spots of bright and dark and bright and dark, the dark bits are absolutely dark, because the wave perfectly cancels there. So this is so important. I want to be sure that everybody agrees with what I'm saying, or at least understands my are you happy with my point? Okay. Now, what happens if I move the mirrors a little bit? Let's move the mirrors up. So here they go. the path is now getting longer. This upper path is now getting longer, and so it takes more wiggles for the wave to arrive here, and the result is that the top wave slides over relative to the bottom wave, and now they cancel. If I move the mirrors just the right amount, I can make these exactly cancel, and there can be no light coming out here. Fortunately, the same thing that made this slippage occur here makes a similar slippage occur here, so these two are now adding up. So the light has somewhere to go, which is important because it's got to come out. It comes out instead down here. So we have a device where we can flip where the light beam comes out by just a small movement of the mirrors. How much do we have to move the mirrors? Well, we have to make the wave move over by half a wiggle. That's it. And I know how far that is because I know something about the wiggling of light. And the answer is, for visible light, that mirror movement is only 0.0001 millimeters. That's very small. It is, in fact, about 1,000th of the width of a hair. So this is an instrument which can measure the most amazingly tiny movements of a mirror. So that's the interferometer. This is by no means the only application of an interferometer, as I'll show you. But the first interferometer I want to show you is exactly like this. Oh, by the way, I've spent most of my life making interferometers of one sort or another, so it will not surprise people who know me that I want to talk about interferometers. They're quite wonderful. In the rest of this talk, I'm going to tell you about 3 interferometers. I'm going to tell you about a kilometer-sized interferometer using light waves to detect gravity waves. That's the first one. The second one is going to be exactly the opposite, really. It's going to be electrons instead of light, and it's going to be an atom-sized interferometer, absolutely minute interferometer. And the last one is going to be in the middle, a centimeter-sized interferometer using a different kind of wave that I will explain, a wave made out of whole atoms. So let's begin with the kilometer-sized interferometer. It's called LIGO, which stands for Laser Interferometer Gravity Wave Observatory. And it's a project in the USA in which 2 huge interferometers were built. Why were they built? Well, long ago and far away, 2 black holes crashed into each other. There was an incredibly violent collision, and this launched a gravity wave that rippled through space. And here is a movie, I hope. Yes. So if you try and look at a black hole, which is black, against the background of space, which is black, you don't see anything. But you can see some green stuff. And what that is think about space like this. Space is a bit like a sheet of rubber. And gravity is a distortion of the rubber. Black holes have enormous gravity. So when they go around each other like this, they stretch and they compress and they do this to the rubber. And that sets a wave rippling out through space. So that's what happened. And the ripple here traveled for 1,300 million years, and it arrived on Earth on the 14th of September, 2015. And we know that because the ripple passed through the LIGO interferometers. This is one of the 2 interferometers, and moved the mirrors a little bit. And here's the astonishing thing. It shook the mirrors of the 2 LIGO interferometers by 0.000000001 millimeters, which, for the scientifically inclined, is 10 to the minus 18 meters. This is a really sensitive interferometer to be able to see that. And what this shows you, there's a blue trace and an orange trace. One of them comes from a detector in the north part of the USA and the other in the south part of the USA. And as the wave came through the USA, first it shook one and then it shook the other. And here they've shifted the 2 to sit them exactly on top of each other. And you see it's the same signal, it's the same pattern. That is the first ever gravity wave detection. That's very exciting for astronomy because up until now, astronomers could only look at light. It might be very blue, or it might be very red, or it might be visible, but it was just light. And now they can look at, which is a wave of light. This is a wave of gravity. It's a completely different way of looking at the universe. So it's very important. Okay, that's the first interferometer. And now I want to come to interferometer number 2, which is using the electron wave inside an atom. If I want to make a device based on electron waves, a very natural place to do that is inside an atom, because as we've seen already, the atom is the home of the electron. So before I get to this interferometer, I just want to consider a little bit more what's inside an atom. Here it is again. Inside every atom there's a nucleus, and it attracts the electron. That's why the electron hangs around. It attracts the electron. Now you know it's a wave, so I can tell you this very important thing. The wave has to fit into the space. So I could have a wave with 3 lumps, or 4 lumps, or 5 lumps, or 6 lumps. But I can't have a wave with 1.5 lumps, because interference will make it go away. It has to fit exactly. So we can have slow wiggles here, or fast wiggles here. Scientists don't like to say wiggle. So we call it frequency, but the frequency just means how many times does it wiggle per second. So rather than calling this slow wiggle and fast wiggle, I call it low frequency and high frequency. Inside the atom, there are particular frequencies that the electron is allowed to have. And this should remind you, or it reminds me at least, of a little musical instrument. If you take a bugle and you blow a bugle, it will only make certain notes. That's why the last post sounds the way it does, because those are the only notes a bugle can play. The wave has to fit inside a fixed number of lumps inside the bugle. So you can think about an atom as a tiny, tiny musical instrument inside which are particular notes that it likes to sing. If I prepare an atom, we'll come in a moment to how you do that. If I prepare an atom in a state where its frequency is high, so I call it F high, it can jump to a lower frequency here, F low, and out will come, marvelous, a photon. That's where photons come from. They come from atoms which are jumping from a high frequency state to a low frequency state. And the frequency of that photon is exactly the difference between the high frequency electron's frequency and the low frequency electron's frequency. The difference frequency is the frequency of the light. So photons are born from atoms doing this. And the reverse works too. If I take a photon of the right frequency, what I mean by the right frequency is it has to be tuned to the notes, to a difference of notes that the atom can sing. So if I pick the right frequency, then it can cause an atom to jump up from a low frequency state to a high frequency state. This coexistence between atoms and photons is very important and fundamental to how many of these devices that I'm describing to you work. So now we're ready for interferometer number 2, and it's called the atomic clock. I'm going to start with an atom of low frequency called F low. I'm going to shine some light on it to make it jump up here. But now, crucially, I'm going to choose the light in such a way that it's a splitter. So I don't make all of the electron wave go from this F low to this F high. I just split it. So here's the wave coming in. The light pulse is a splitter. And after the light pulse, part of the wave has frequency F low, and part is F high. So here I can draw for you a wave that is wiggling at frequency F low, and here is a wave wiggling at frequency F high. And at first sight, there's not much obvious difference between the two. But let me slide the one up over the other, and you'll see something quite interesting now. They're in step here at the beginning. That will make a strong wiggle because they're in step. But if you get to this place over here, they're exactly opposite. And the reason they're opposite is because one of them is going faster than the other one. So they get further and further out of step until here. They're perfectly out of step. And then it carries on so that they come back into being in step here, and then out of step, and then in step. So if I draw what the whole disturbance looks like, it looks like this. This is like the tick-tock of a clock. So now I have a little demonstration, just in case you didn't follow or believe. I've got here the two, they're not really the two electron waves, but they're like the two electron waves. They're two sound waves. So this is F low here. This is sound of low frequency, and this is sound of high frequency. And I'm going to play them both together, hopefully. Okay, I think you can hear. There's a high one and a low one. And there they are both together. And now if I bring them close to each other, can you hear that? It's going wah, 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 wah. And if I make F high be a little higher, now it's wah, 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 wah. I think it depends a little bit where you're sitting. When I tried to set this up earlier today, it was much clearer for some people than others. Can you hear it? Yeah. That is the atomic clock. It's not. It's a sound wave. But that is the idea that makes the atomic clock work. So let me just finish the story of the atomic clock. We've split the electron into a fast wave and a slow wave. Now the wave is doing this. And I'm calling this tick-tock, tick-tock. Your ear did the job of superimposing the two waves and seeing what you get. In order to finish this off with my light and my electrons, I need a combiner. I need another pulse of light. And now you must surely recognize this. This is an interferometer again. And when I read this interferometer out, I hear this tick-tock, tick-tock of the clock. And the frequency of that is just the difference frequency, F high minus F low. And as I've written here, the ticking of this clock is fabulously regular. And that is because it comes from the inner workings. It comes from the guts of the atom. And the atom is an incredibly stable thing. Here's an atomic clock. You can buy one. The atoms live inside this tube, inside a vacuum in this tube. Some electronics. That's a 19-inch rack. It's like this. It's a standard size for plugging into a rack of electronics. And this one you can buy on eBay for £10,000. Who needs an atomic clock? You do. Yes, you do. For example, your phone call. These are people in London all wanting to telephone Glasgow on their phones. You can't all have your own individual link from London to Glasgow. So we have to do something to efficiently pack all these phone calls into a limited number of links. So I have here what's called a timing unit. It's basically a clock. And the clock picks off packets of your phone call and puts them efficiently onto the link that goes to Glasgow. And when they arrive at the other end, another timing unit picks them off again and sends them to where they have to go. This will only work if the clock in this unit is very well synchronized with the clock in the other unit. Otherwise, it will get confused about whose message is whose, and it will send your signal to the wrong place. How good does it have to be? Well, it needs to be good to 1 second in 3,000 years, or 1 part in 10 to the 11. That's very good. That's an atomic clock. There's no pendulum that will do that for you. Even more challenging is the sat-nav. So when you're driving around in your car and it tells you within a few meters where you are, what it's doing is sending messages back and forth to satellites. And so if you measure how long it takes to send a signal to a satellite and receive a reply, that tells you something about the distance between you and the satellite, because light takes time to travel from A to B. If you know how far away you are from several satellites, then you can work out exactly your position. But to know it to within a few meters, you have to have a clock which is good to 1 second in 140,000 years. That's 1 part in 10 to the 13. That's even better than this. you need atomic clocks for that. That's how it works. So every day when you travel around, you are benefiting from the quantum technology of little interferometers made from electrons inside atoms. It's not just good for technology, it's good for science. So I want to give you one example. I mean, there are many other examples of why we need clocks, but I'm going to stop with that. For science, here's an interesting question. We have what we consider to be laws. So we write down some equation that says, this is how it is. And there's an obvious question, okay, that's how it is today, but will it be like that tomorrow? And was it like that yesterday? Well, with these amazingly accurate clocks, you can try to answer that question. So a science use is testing the constancy of physical laws. People have compared the ticking of different atomic clocks. All of these atoms can be used to make clocks: cesium, dysprosium, mercury, aluminium, strontium, ytterbium. The ticking of the clock has a different rate in each one of these atoms. Some of them are quite low, like cesium. Some of them are very fast, like strontium. But these clocks all tick with each with its own particular frequency. Now I can make several clocks and compare them and look at the ratio of their frequencies and ask, is that constant? Does that change over time? And the answer is they're astonishingly constant. And the only way we can understand why those frequency ratios are constant is if the laws of physics, which tell the atom what F high and F low it must have, if those laws are not changing over time. So the result of experiment is that these frequency ratios change by less than 1 part in, I don't even know how to say this now, 10 million billion, I think it is. Anyway, 10 to the minus 16. It's 1 part in 10 to the 16. It's amazing. In fact, a better way to think about it is, so these experiments have been done over the last 10 or 20 years. But if I imagine that there is a change and it's happening steadily over the whole lifetime of the universe, it would mean still that the laws of science or laws of physics have not changed by more than 1 part in a million since the beginning of the universe. So we conclude that the laws of physics are not changing. Well, this brings me to a natural remark to make. Why atoms make spectacularly good sensors? Well, the first is that they're constant, as I've just shown you. Those electrons don't get tired. They just go round and round for a million years, exactly the same. They're identical. If you compare one cesium atom with another cesium atom, they behave exactly the same way because they're stuck together by 3 very simple ingredients following a very simple law that is not changing. So they're always the same. So they're calibrated. And then, of course, the fact that the electron is a quantum thing whose motion is controlled by waves gives you the chance to do interferometry, and that makes them very sensitive as detectors. In this case, I've talked about the detection of time, but there are other things you can detect, which I'll mention briefly in a minute. And the last point, which I think is an important one, is the symbiosis between atoms and light. So the atom is a little isolated chronometer or whatever sensor you want it to be, but it can speak to the outside world through light. So you can shine light in to prepare the atom and make it work the way you want it to. You can use the light to probe what it's doing, and this way it can interface with the outside world. And I think this symbiotic relationship is important for making the atoms into a useful sensor. So now the last interferometer I want to tell you about is for sensing tiny forces. In my lab, we use laser light to cool and launch a cloud of atoms. So I won't say anything about the details of this, but this little red ball that you see is a real photo, a CCD camera picture of a cloud of atoms in my lab, which have been cooled and launched, and they're falling down because of gravity here. Each atom in the cloud travels as a wave. Now, I'm not talking about an electron wave, and I'm not talking about a light wave. I'm talking about a whole atom wave. And we make an interferometer with that wave. The splitters and mirrors of this interferometer are laser light. So it has a rather appealing symmetry with the first interferometer I told you, the LIGO interferometer, where the wave is light and the splitters and combiners are made of matter. Here, the wave is matter and the splitters and combiners are made of light. So we have a pulse of light, and what it does is to split the atom wave into 2 bits. And then after some time, we have another pulse of light, and the job of this pulse of light is to be the mirror. What does the mirror do? It pushes the 2 waves back together again, like so. And after a second time interval, t, they come together here. And now I've got to make the waves overlap with each other to interfere, and so I need a combiner, which is another laser pulse. And then finally, there are the 2 outputs, and I can determine the difference in how many wiggles went along this path and how many wiggles went along this path by measuring whether the atom came out path 1 or path 2. Now, it turns out that this instrument is remarkably sensitive. It can sense a change, a tiny force equal to 1/1000th of gravity. So if this gravity here were to change by 1 part in a billion, it could be sensed by this interferometer. And you are supposed to say, wow. That's a very sensitive device. What can you do with it? Well, one thing you can do is called inertial navigation. And what I mean by this is Lewis Hamilton sitting in his Formula One car. When the car accelerates, the driver feels a push. I'm sure you've all felt this. You feel a push in your back. And that is caused by the fact that the car accelerates. And that's called inertia. So that force that you feel on your back is exactly the force that the atom interferometer can measure. So if I put into the racing car, I'm not going to do this, but if I put into the racing car an atom interferometer, I could measure Lewis Hamilton's acceleration. And if you know the acceleration of a vehicle at all times, there's a simple mathematical procedure which allows you to calculate position. Well, okay, if I'm in Formula One car, I just look at the track, I know where I am. But if I'm on a ship, for example, I need some information to help me know where I am. So you can navigate with atom interferometers. Here is one, just to give you an idea what they look like. This is one being developed in my lab for navigating ships. And that's the size of the thing. It looks a bit complicated with a lot of wires. When we exhibited this at the Quantum Showcase earlier at the end of last year, we put a big box over it so that it looked very simple. But of course, there are actually some wires and stuff. A perfectly reasonable question for you to ask is, why not just use sat-nav? And the answer is, satellite signals are very easily jammed or faked. So somebody who wants to steal your cargo can actually hijack your ship by fooling the sat-nav. So it's very good to have a way of navigating without this risk, and atom interferometers will allow that. There's another neat application I had to tell you. I've actually I'm not 100% clear how much time I have left, but I think I have enough time to tell you this.
Yeah, about 8 minutes.
Ah, perfect. So there's what I think is a really neat application to cosmology. Cosmologists, there's people who try to work out what the whole history and development of the universe is, use information from astronomers about what's out there. And what we know is that the universe used to expand slowly, but now it's getting faster. So the rate at which the size of the universe grows is increasing, it's accelerating. And nobody knows why. So the unknown cause of this mystery acceleration has been called dark energy. It's a marvelous name, it just means I haven't got a clue. So theorists theorists try to work out what could it be, what is the cause of this dark energy. And one idea had as a kind of I can't think of the word to say, as a side byproduct of this idea was that there would be a new force of attraction between an atom and a ball. So here I have a vacuum system with an atom inside it and a ball nearby. And this theory, which would be great because it would explain what dark energy is, would have to produce also a force between an atom and a ball. So the way science works is a theorist says this thing is going to happen, and then you check to see if it's true. So we decided that we might be able to check to see if it's true. But of course the first thought is the dark energy force will be very, very small. However, atom interferometry is very, very sensitive. So in fact, it turns out that one can be sensitive enough to detect this force. And our experiment shows that there is no such force. So that theory's out, and that's how science works. And what's satisfying about it is a little tabletop experiment has helped us to understand the behavior, I mean, not all the behavior, but something about the behavior of the whole universe. I've tried to give you a flavor of what quantum means and how it can be useful in technology and in science. And in choosing my topics, of course, I have missed out many important things. And some of them I think were so important that I just had to say a little about them. So here's very little about them, just to give you a feeling. Electron wave interferometers inside atoms, like the clock. You can do them slightly differently so that they're sensitive to magnetic fields. Why are we interested in magnetic fields? Well, one nice example is in your brain, while you're thinking, while you're trying to work out what I'm telling you, electricity is flowing in your brain, and that makes a magnetic field around the outside of your head. And you can measure that. So psychologists and medics can measure that and can learn something about how the brain works. And quantum interferometers are a very good way of doing those measurements. You can also measure electric fields, and electric fields might be interesting, for example, if you want to have communication at very low power. So first of all, let's all try and save power, that's great. But the military is very interested too in communications at such low power levels that nobody can listen in. And that is possible with extremely sensitive measurement of electric fields. Another thing I want to touch on is the use of single photons. So I told you earlier that the elementary particle of light is the photon. A famous and a very interesting application of that knowledge is a method of secure communication. So I'll just give you an idea of how that works. Here Alice wants to send a message to Bob. The crucial step is for Alice and Bob to agree on how they will encrypt their communications. So they need a code, they need a rule book. For example, they might agree that every letter in the alphabet is going to be replaced by another letter. And once they know what that is, then they can send a longer and more complicated message, but the starting point is to try and get the key across. Well, in conventional communication, Alice would just phone up Bob and say, this is the key. And the problem with that is that Alice would be sending many photons to Bob, and then Eve, who is not surprisingly the eavesdropper, Eve can steal some of those photons to listen in, and nobody will know. So the trick about quantum communication is that Alice will send each single bit of information on just one photon. And why that's important is that one photon cannot be copied. I don't have time to discuss why or how, but you cannot copy one bit of information that's encoded on a single photon. And so if Eve takes the photon, it never arrives with Bob, and it does not become part of the key that they wish to share. And if Eve doesn't look at that photon, then Bob gets it, and it can be part of the key that they share. And that makes it possible to have a 100% secure key. So obviously there are many applications in banking or the military, or anybody who wants to send private messages could hope to benefit from this. The last application that I cannot ignore is the quantum computer, because that's the one that everybody knows something about. So let me tell you what the general idea is. In a conventional computer, you have bits of information which can be set to be either 1, like that, or 0. So the bit is essentially like a switch, and it can either sit this way or this way. And that way it will represent a 1 or a 0. So if I have a group of bits, I can represent a number, for example, the number 1001000100011. And if I flip the switches differently, I can represent a different number. But I can only represent one number at a time. Now here we come to the quantum bit. The quantum bit can go through a splitter. And after the splitter, the wave goes 2 ways. One way can represent 0, and the other way can represent 1. And the wave is going both ways simultaneously. So this quantum bit has the ability to represent both 0 and 1 together. And that means that a group of quantum bits can represent a great many numbers all at once. That's the key to the thing. So now if I have many such waves representing many numbers simultaneously, they can be made to interfere with each other and perform computations. And the beautiful thing is they can perform an enormous number of computations all at once. And so if you looked at the poster advertising this talk, it had this picture, which has nothing to do with quantum computing. But it just reminded me of this idea, of this quantum computing idea, of many quantum waves all swirling around and interfering with each other, and somehow agreeing in this region over here on an answer, where the wave is strong. In theory, this is important because it can solve problems that are too hard for conventional computers. It's not necessarily going to be fast. It's not going to replace your laptop. But what it's going to do is allow you to address problems that your laptop cannot address. And so that's very exciting, but it has yet to be achieved. That's the status of that. So in summary, understanding electrons and photons has profoundly changed the way we look at nature. We now know that the motion of particles is governed by waves, and that the waves explore all possible paths simultaneously. This knowledge is transforming society through inventions. We've talked about some, like the atomic clock for satellite navigation and high-speed data. Other examples, inertial sensing, quantum messaging. And new devices are still being developed, famously the quantum computer or quantum simulation, giving us a new order of computing power. And also, quantum measurements have transformed science by giving us the ability to make incredibly precise measurements of energy and time. We study matter, light, space, and time with spectacular precision, and that has given us a deep understanding of all the particles and fields in our world. Don't think for one moment that we know everything. Especially, I want to address this to young people especially, because I remember a certain stage when I thought all I was doing was receiving knowledge from people about a topic that was already over. This is not the case. There are big physics questions that still need to be answered. We do know. I mean, my talk has been about the fact that we know very precisely how to describe electrons and photons. In fact, I couldn't resist putting up this. This is an equation. This is called the Lagrangian of quantum electrodynamics. It's an equation with the most astonishing predictive power. It will predict quantities with an accuracy of a part in a billion. It tells everything that I've told you is hidden in here. And so you should see that this is how physicists think about it. Also, I thought you might feel a little smug to recognize this here, mc squared. But here is the composition of the universe as far as we know it. This is a pie chart. The yellow bit, that's 5% of everything. That's the normal matter. That's the stuff that we began with, the animals and trees and birds and air and stuff that we live with. Okay, well, we understand that. But astronomers know from the way that stars and galaxies move that there's a lot of stuff out there which doesn't shine, it doesn't produce light, yet it must be there because it has gravity. And that is called dark matter. And we don't know what it is. And then we've already discussed the idea that the universe is expanding at an ever-increasing rate. That's the dark energy. We don't know what that is either. And furthermore, although we have this wonderful equation to tell us about electrons and light, we don't know how to fit that into the theory of gravity. How does gravity fit in with quantum physics? There's an awful lot we don't know. So for young people who find this topic interesting and would like to go on, please do, because we need you. That's it.
Well, thank you very much, Ed, for a wonderful lecture. I'll say one or two words at the end, but once we've had an opportunity to give you an opportunity to ask Ed some questions. So who would like to kick us off with a question? We have one over here. We've got a couple of runners with microphones, so please just wait until the microphones got to you.
Hello, thank you very much. I've heard about quantum entanglement, and I almost think I know about it. The puzzle in my mind is, could this phenomenon form a basis of faster-than-light communication? If you've got a thing here which is affected by what you do to something over there, can you use this to communicate?
Yeah, it gives the impression, doesn't it, that you can. So just to, in case that not everybody knows about this, you can arrange to have two particles, let them be photons. You can have two photons, and they're either polarized up and up like this, or they're polarized down and down like this. And you have two detectors far apart. And the photons don't know any more than we know whether they're up or down until there's a measurement. It's just like when I showed the photon landing on the screen. Nobody knows where it's going to land until it lands. So there's a detector over here, and the detector over here says, this one was polarized up. We immediately know that this one must therefore be polarized up. And if we later check whether that was true, it was true. But if exactly the same experiment says it was polarized down, then that implies immediately that this one was down, and when we check, it was down. So the question is, does that mean that some information has been communicated from this particle to this particle, and because it was instantaneous, was it communicated faster than light? And my answer is no, I don't think it was communicated faster than light. I think it's just that that's the way quantum mechanics works. If you try and dream up a scheme for actually sending information from Alice to Bob using this faster than light, we don't know any scheme to do that.
Okay, who else have we got? He's got a burning question here. Yes, right in the middle on your right. Just wait for the microphone to get to you. Keep your hand up, well up in the air. Yes, that's super. Thank you.
Hi, I had a friend in Vancouver who worked for a company called D-Wave, and she told me many years ago they had a working quantum computer. Was that a lie?
Yes.
A number of labs have devices that have the ability to compute using quantum behavior, but what no device has, to my knowledge, is the ability to compute anything that cannot be computed more quickly than with a classical computer at the moment. So the promise is there for a device that can solve problems that are too difficult for classical computers. But in reality, right now, the state of the development is such that no computer exists, no quantum computer exists that can solve anything better than a classical computer. And there are technical reasons why this is hard. So D-Wave has a machine that uses quantum mechanics to help them do some kind of computation, but it doesn't deliver the dream of solving problems that are too hard to solve with your laptop.
Okay, we have one just behind you there. There we are. Great. Remember, there are no stupid questions. There are only stupid answers. So you can't be stupid. He can be stupid.
I'll try not to.
Please go ahead.
So I was wondering, with the detector at LIGO, how do they know for how long the wave was travelling before it reached Earth?
Can you just say again? I didn't quite catch what you said.
With the detector at LIGO,
Yes.
how did they know for how long the wave was travelling before it reached Earth?
So, how long did it? How did they know how long it was travelling since the big explosion of black holes, or how did they know how long it took to get from the one detector to the other? The first one. Very clever people looked at this little wiggle and inferred the movie that I showed you. So from the movie, they were able to work out so from the frequency of the oscillations and from the magnitude of the oscillations, they're able to work out how big the black holes must have been and to work out how they spiraled in and coalesced. And then from the strength of the signal, how far away that must have been in order for the signal to be so weak by the time it arrived here. It's all done by modeling on the basis of these little wiggles. Does that answer your question okay?
We have a hand up, sort of, I guess, 2/3 of the way back on my right, your left.
Hi. I was just wondering how metamaterials work that bend light around themselves.
I can't see where you are.
Oh, you think she's a plant? Very good.
The problem I have two problems. One, the world's expert on this topic is sitting right here. The other is I can't see a way to answer you satisfactorily in a short amount of time. I will be happy to talk to you immediately afterwards if you like, but I think in this forum it doesn't make sense for me to try and answer that particular question. I'm sorry.
Okay, that's fine.
Anyway, we've got one right down here on the front. I'm still going to ask you to wait. Sorry, I know you're close to him, but everyone else wants to hear your interesting question. So let me just hang on a second. Here we are. Over here.
Hello? Ed,
Hello.
When you set out to build an interferometer, what are the biggest challenges you face, say, for example, with a clock or your gravitational measurement device?
That's a many-faceted answer to that. I mean, the first problem is it costs money, and at the moment you need quite a high level of scientific expertise. So you have to get a team of people who know what they're doing, and you have to get money. A key thing is laser technology. So all of these things that I've spoken about could not have happened without the progress, amazing progress of laser technology. So you have to have laser systems that are able to prepare light sufficiently, exquisitely well for the instrument to work. That costs money, but also it's just a question, is it even technically possible? So, for example, the navigating interferometer requires lasers which are at the forefront of what laser technology can do, and we work very closely with a laser company that specializes in making scientific types of laser. Then you think very hard and try and work out what's going to go wrong, and then build it. And at some point, which is more or less now, the device is sufficiently sensitive that you can begin to think about commercializing it and making it into an instrument that people can use. The atomic clock is much older. Atomic clock is 40, 50 years older and had a similar evolution over more than a decade to become a useful practical device. So there are many strands to your question, but it's money and people and understanding the science and then turning it into a real instrument.
Okay. we'll have one last question down in the front here. Gentleman with the green shirt. The microphone is just coming to you now.
Hi there. How do you capture a single atom and cause it to be used as a machine? How do you hold it?
Yeah, so I said so very little about that, though it's a subject close to my heart. So we use the laser light. So we begin in the interferometer that uses whole atoms to navigate. I showed you a little red blob doing this. That was a cloud of about 10 million rubidium atoms in a vacuum system. So we pump all the gas out of a vacuum system. We then release some rubidium vapor by heating up some chemicals. And then we use laser light to collect and cool a cloud of these atoms. And at this point, although we have 10 million of them, they occupy several cubic millimeters. So the density of atoms is actually quite low in the sense that they don't often bang into each other. They're not going to solidify and fall out as a lump of stuff. So it's an ensemble of almost completely isolated individual atoms. When we interrogate it and use it to make an instrument, we talk to all the atoms at once with our lasers. We read them out all at once. But each one is an individual interferometer. But we never, in that experiment, we never look at one atom at a time, which I think is what you were asking about. We could look at one atom at a time. And the way that we do that is to scatter light. So it turns out that these atoms will scatter light at a rate of 10 or 20 million photons per second. And that means you can get enough fluorescence from the atom to see one atom if you have a really good camera. And some of these clocks that I mentioned to you are actually made using single atoms, usually ions, where you just look at one. And again, it's suspended in a trap in a vacuum. Does that go some way to explaining? Yes. Yeah.
Okay, I think we probably have to bring it to a close at this point. I want to thank Ed, first of all, for sort of pulling back the curtain for us on the fascinating world of quantum physics. And as he mentioned, electrons and photons are very simple particles in many ways. They're all around us, and yet they're a lot of highly complex physics. And it's a real art to translate complex physics like that into the sort of lecture you heard today, where you can really make it accessible to a wider audience. And so we're deeply grateful for Ed being able to do that for us. I guess many of you will have added another word to your lexicon, interferometer. I bet you'll never forget it after this lecture. So please join me in thanking Ed again for a wonderful lecture. Thank you very much.